I'm delighted to be here with you to talk about digital twins for semiconductors. I know you have had some introductions already on the physical side of semiconductor, be it design or manufacturing, how the industry works. And I wanted to talk to you a little bit about the digital twin enablement of this big revolution that is going on in semiconductor industry. And it's a very scientific based digital twin revolution that is going on. And so I wanted to start with what we do at Dassault Systems a little bit to give you a perspective of the range of technologies that will make it happen. But at Dassault Systems, really start with the belief that the virtual worlds extend and improve the real world, right? And so that is serving the next generation of virtualization needs across all the industries that are underpinned by the semiconductor technology, and that you have ultimately these connected multi-scale set of digital twins that are ultimately driving the next level of innovation there. So in order to make this all possible, at Dassault Systems, we have a platform, a digital twin platform. It's a scientific virtual twin experience platform that serves various domains of capability, from design to collaboration to simulation and manufacturing and data intelligence. And in order to really serve the larger industry, so we serve 12 industries from various industries in manufacturing, from automotive, aerospace, high-tech, semiconductors, all the way to life sciences. But it's a complete ecosystem approach. So we do serve with educational networks, with the specific software offers, startup lab innovation accelerators, and also specialized assistance for hardware startup programs, with a turnkey software offer. So it's really a very connected set of capabilities that all come together on the platform to deliver the next revolution in semiconductors. So a little bit of my background in semiconductors. So it's fair to say probably I've been living and breathing the semiconductor ecosystem since last year with the advent of the CHIPS Act. Many of you probably heard about it, the big investments that are going on there. And as part of this pursuit, we are having this very integrated approach for virtual twins development. And even before the whole revolution in semiconductors with digital twins started to happen, I have had really this intersection of experiences coming from automotive and aerospace, where the digital twin technology has been very advanced and mature. If you look at the crash tests, or many kinds of other physical tests, that have been moved into the physical realm, and also a lot of developments in manufacturing digital twin, virtual factories, or this particular focus on getting the integrated product and process right, and of late, semiconductors and electronics, with automation and robotics all coming together to that. So I'll be sharing with you numerous examples of what is digital twin. Again, there are a number of definitions possible, so I want to make it kind of conversational with you, so give you a glimpse of all that is going on there. And the great news is that this field of digital twins is just getting started. With this confluence of factors, call it as a perfect storm, wherein the semiconductor industry, the chip makers, the foundries, so they're completely rethinking the whole supply chain. There is a lot of focus on onshoring, reshoring. There are also very new kinds of semiconductor applications, for automotive, data centers, right, and life sciences. So this focus on system level solutions is also increasing the complexity. Workforce of the field. You are, with the interest you are taking, you are going to be entering the workforce with potentially new roles and new personas that don't exist today. It's not just about AI cloud, but many others. That are, so with that, and then we have the thrust from the government. Wherein there have been specific programs. That are being launched. There is a dedicated institute for digital twin institute for semiconductor manufacturing. One recently that was launched was AI Institute for Resilient Manufacturing. And then just yesterday, another $100 million worth program was announced for AI and automatic experimentation for sustainable semiconductor materials, right? And this is all gearing towards this need to transition successfully from the lab to fab, nurturing the innovation process, which often, gets stuck because of prohibitive cost of manufacturing and also the time it takes to transition it. And then thirdly, we have the consortia, such as semi.org. They are big on interoperability. Standardization is very, very important in semiconductor industry. So the same thing is true for digital twins. And then we have dedicated consortia like Digital Twin DTC that is also putting a lot of emphasis on interoperability. So it's really a very interesting time to be into this subject. The first chapters are being written, but the book is still to be written. And the three big pillars that are really in front of us are in terms of building the workforce of the future. There is this focus on process experimentation. How do you scale the processes and accelerate the innovation, and then sustainability, right? And how do you enable that through digital twins? Again, there are a number of definitions, and this is beyond this discussion to get into that. But if you look at the whole evolution of digital twins, again, a lot of early efforts, started with 3D models, models of the fab layouts or equipments, and performing general simulation, mechanical or electronics type simulations. And then we started to have the data connectivity thanks to the IoT and the cloud platforms, more sophisticated multiphysics, combining various phenomena in mechanical with electrical and electronics phenomena. And then now with the democratization of AI, now we have this third phase, if you will, that is now, which is combination of hybrid digital twins, combining physics, first order principle physics that you are all going through, as well as machine learning based on the data that is starting to come back from the semiconductor fabs as well as test sites, and having this bidirectionality between the two, the physics actually augmenting the machine learning algorithms, and the machine learning, helping improve the physical results. And then eventually this digital twin then affecting the actual semiconductor manufacturing process in a predictive way, and to be able to control that, right? Just in a nutshell, there are again number of variations of this theme of what is a virtual twin or digital twin. But the way at Dassault Systems, we specifically talk about virtual twins because often you have certain objects, that are modeled, simulated, and experienced even before the physical thing comes into reality, right? And it's so throughout the course of that product. So it's important to think of digital twins even before the physical thing exists, right? But in a nutshell, we have this combination of the virtual plus real. So we have from the physical entity, an equipment or sensors, so you capture the data, and then combine that with the various types of behavior models, different types of physics, and then be able to simulate, learn from that data, and then affect the virtual what is going to be the future, right? And essentially having this bidirectional loop of the AI plus physics, kind of complementing each other. So in order to do that, again, there is going to be this massive scale of physics that is necessary in order to have high fidelity, accurate simulation behaviors. And So these are just some of the examples of various, phenomena that are essential, whether it is structural, electromagnetics, fluid flow, thermal, and at various scales, right? So again, if you have had not only the engineering, but you may have, physics background, you may have, chemistry. All these topics, are going to be essential in terms of, putting together this holistic, modeling and simulation efforts. Same thing for materials. Materials is going to completely change the whole semiconductor device designs as well as manufacturing process. And so with the modeling and simulation technologies that are available now, you are able to predict the properties of the new materials. You can validate if the materials are going to actually perform as they are expected. And there is this continuum of, again, material chemistry, so atomic level, molecular level, and then at the discrete, element and then component and all the way level. So this is really, think of in digital twins, when the scientific angle, think of the material science, chemistry, and physics all together, right? So I'm going to give you a series of examples of various digital twins depending on the use cases. But the one way to think about those is also this connected virtual twins. So we have the chip as the product, right? So we have from the materials, you have the chips. Then the chips are put into packages, and the packages then and the chips are assembled on the boards. And then from there on, they become part of the end system, whatever that system is, right? Same thing for manufacturing. So you have, again, from materials that are used in manufacturing up to the process. There is the fabrication equipment that executes that process. And then you have all those processes and equipment that are put together in order to execute the whole flow in the fab. And then there is the ecosystem. But I will just focus on the product and manufacturing examples for now. But what's important is that they are really built on a strong foundation of this science from physics and chemistry, in the whole discipline for continuous modeling and simulation. Data science also, this is a key discipline for you to consider here in terms of augmenting these physics models with data. And then there are a number of technologies, but the data science discipline is also very critical. Still, there is human in the loop. There is human expertise that is crucial in order to take the best advantage of the AI technology. So part of that whole platform thinking for virtual twins is also the human collaboration in the loop. Okay. So then just moving into the product twin examples, right? So we talked about from materials to the semiconductor design. Then at the package level you may have MEMS. So MEMS are the different types of sensors that are put on a semiconductor package. Then there is the whole package design. And then finally taking the chip and putting that into the actual electronic system. So all the performance of the chips, whether it is electromagnetics interference, or if it is thermal management, or structural issues, there are all kinds of physical phenomena. And now with the chips actually being part of not just our phones or general consumer devices, but also in a very mission critical environment like airplanes and cars. So there is the even increasing phenomena of simulation and modeling that has to be performed there. So then moving specifically into the package, right? You may have heard about advanced packaging now. Is really a big thing, wherein you bring in very heterogeneous chiplets, of different functionality, and then they're integrated. And so that is, again, increasing the level of sophistication and the complexity. So there are a lot of thermal issues. There are reliability issues in those packages. Again, signal, power integrity, fatigue, vibration. I mean, just unprecedented amount of phenomena that to look into. And the traditional approach is always, hey, I'm going to just create some prototypes, build those prototypes, test, find issues, come back, redesign. I mean, that cycle is just too expensive. And now we have these increasing models that are allowing you that level of fidelity that you can avoid these physical tests. Okay. So moving on to manufacturing. Again, similar thinking, so think of digital twins really not just as discrete, small projects, but ultimately to get the true value, this connectivity from materials. Again, in this time in the manufacturing process context, the process itself, you have there is a large number of processes that are performed on a wafer to completely fabricate that. And then there is the packaging side of the process also. There are equipment, again, very, very costly, capital equipment, $100 million upwards. And then you have to establish the whole process flow and then put that in operation in the fabs. Right? So I'm just going to go through some of the examples here. So one thing that I will just pick up here is this whole atomic level modeling and simulations, and that allows you to understand the material structures. Again, there is the physical phenomena that is always going on. There are material testing and material research labs, wherein all this testing is happening. And again, the idea is to shift left with virtualization and having these accurate models so that you can predict the behaviors, and you have a lot more in the virtual space, a spectrum of possibilities for trade-off studies and so on that you can make happen, right? Again, there are very, very specific examples, but again, for instance, in the atomic layer deposition, you have quantum modeling effects that can be studied. There is also the specific example of silver surface, right? The QMD, quantum molecular dynamics. This is again the field is just opening up actually for semiconductors in terms of digital twin enablement. So then moving on from materials to fabrication process. So we have, again, this is just a very simplified representation of some of the processes, where with modeling and simulation, again, you can predict the behavior of some of these processes: deposition, lithography, etching, ion implantation and doping, and CMP or planarization. So these are processes, that take a lot of time to converge, because of extreme variability of the process. So even if you follow the exact same recipe, you may or may not get the results. So therefore, often it's much more economical to perform these virtual experiments, with using the digital twins. Okay, so I'll take one specific example of the process here. It's called the CMP process. Again, you can see the kind of behavior you can visualize, using the simulation models. And this is the case, wherein there's a significant, wear that can happen on the pad and the silicon wafers. That all can be predicted. Okay. Then moving on to the packaging part of the process. Again, this is a very simplified representation of one particular type of package. So what if, again, we can simulate some of these processes, capture the behavior, and predict the performance ultimately. Okay. So a lot of multiphysics, thermal is, again, if if you have one takeaway from some of these examples, thermal is a big issue. Thermal interface materials on the packaging. Okay, so from there, let's move to equipment. Okay, so these are again many different types of digital twin studies you can perform on the semiconductor manufacturing equipment, right? This is one example wherein from a engineering and validation perspective, you can run multi-physics studies on the particular behavior that is the process behavior that is going on inside this equipment, conduct the design of experiments, even optimize that before you start to build the prototypes. And after that, there are again number of use cases wherein you can use that equipment model to build work instruction, how to build that equipment, or if you want somebody to service that, diagnose issues. How do you go about disassembling and analyzing, diagnosing issues? So the idea is you create these twins once, and you use them many times, not to have to create one for each specific application. So this is the approach that the industry is moving towards. Okay, so then moving on to the next level, which is at the fab. Okay, so one example is that so you have built a process on a particular equipment, and you build a complete sequence of the processes, and start to predict how the process will behave, right? We're using the same, whether it's 3D and it's physics, and the sequence of the process. Before you actually go and commission that equipment, I mean, again, think of this gigantic equipment, very expensive. You don't want to take time going and doing trials in the fab, right? You want to validate as much as possible in this virtual space. The other example is the factory floor simulations, right? So having built these unit twins, so you have had unit twins of the fabrication process, the packaging process, you have had twins of the equipment, right? And then there is the whole infrastructure that is supporting a fab, right? It's not just the clean room. There is the whole sub-fab, wherein you have all kinds of, critical equipment that is supplying ultra pure water, the quality of the air, ventilation, and so on and so forth, right? And so then you build this kind of fab level virtual twin, right? And you can perform then many different types of studies there. You can study the flow of the wafer as it flows through. You can study what happens to the certain critical, like there are certain automated material handling equipment so what if there is some blockage on a particular equipment that stops the movement of the wafer, right? And then completely optimize this flow based on, again, you can have in the same fab many different types of chips that could be produced. Gone are those days wherein you kind of build the fab just for one thing and keep on doing it. Now the diversity is there. So there are many different scenarios that can be enabled if you have this kind of a more complete definition. Okay. Then I want to talk to you a little bit about the different use cases based on these same models that we just looked at it somewhat from an engineering, industrial engineering or process engineering perspective. Could we reuse them for virtual education or new workforce development? And there's going to be there's a prediction that some 67,000 roles might not get filled actually by 2030, and many of them are either research engineers or manufacturing technicians. So this become crucial actually to enable that scaling through digital twins, right? So I want to talk to you about the partnership, with Dassault Systems and Purdue has had. I was here one of those days in last winter, wherein with the semiconductor task force here, we kind of envisioned this idea of working with the Burke Nanotech Center here and starting to build a virtual replica of that. And so, of course, it's a big undertaking, but we have been able to put together a pretty interesting, compelling showcase there of a portion of the Burke center, wherein you have not only the layout but also a particular equipment with its models, the process on it, and what you see there is actually the digital twin of that particular portion of the Burke Nano Center. And then on top of it, then it becomes very incremental actually to have immersive experiences. And so shortly I'll show you an example of how you could actually experience all that on an Apple Vision Pro. We have actually that already possible. It's a very incremental effort after that. Okay, but it's real. What I want to say is that do see these type of showcases, so that you can relate to that. Do take an experience of actually having a walkthrough first, and then virtually experiencing these facilities, right? Then so we continue to work with Professor Xiong Chen and the team at Burke. So on the left you see.
My name is Tim Miller. I've been here for 42 years doing this or something like it.
Okay. So this is actually a portion of one of the Burke specialists actually who is giving instructions. So on the left, by the way, is what you see through the Apple Vision Pro, right? And next time I think we'll figure out a way of bringing it here so you can experience it. It completely changes your perception of the whole digital twin, and you can enable training, simple training on equipment. On the right side, you see the gowning and safety process. So if you have been to a clean room, again, it takes a while, right? To go suit up on the bunny suit and go through the whole safety procedure. So the idea here, and then you have it's a facility with it's a precious resource, right? So at some point, not everybody may be able to access that.
You're supposed to hear the cleaner.
Yeah. So the idea is to do this training virtually and then enter the clean room, right? And that way, the idea is that the onboarding time from what it takes 2 hours, it could be down to 15 minutes. I mean, think of it like you can have 10 times more number of students actually accessing this. Okay. Maintenance, right? We talked about those equipment, the capital fabrication equipment, very, very expensive. Even an hour of unplanned downtime can translate into millions of dollars of production loss. So this is not a semiconductor example, but the idea is once you have a digital twin of a particular equipment, and with AR VR technologies, right? So you can actually augment what you see in front of you with work instructions that are very, very precisely oriented. So you get a situational awareness and are able to perform the job much quicker and more accurately than otherwise. So the same idea extends into when trying to maintain a semiconductor equipment or diagnosing the root cause issue. Okay. We have to talk about AI, and so AI is going everywhere, but it's also going into digital twin space. There are a number of things to talk about, but one thing I wanted to talk about was this augmentation of the physics models that we saw up until now with machine learning, right? So this whole new discipline that has just come up, it's called surrogate models. You got to check it out, actually. It's fascinating. I mean, it's really, surrogate models is the AI for engineering, simply speaking. So the idea is to see, well, you do simulations, okay? And the simulations, on one hand, are very accurate, reliable, and that, you can, if you put the right people, you can predict the results and get the job done. But they are computationally very expensive, and they take too long, hours sometimes, depending on the particular physics. So what if, you can use machine learning so that it will learn, or it will find out, reduced order equations of physics, reduced order models. And with that, you can run that much faster and much more economically. So there are, again, a lot of investigations going on in terms of, what is the best fit for surrogate models. You can do this for design space exploration, like very quickly. If you are at, there are a number of design choices in whether it is chip design or board design. How do you kind of narrow down that funnel of possibilities, with surrogate models? Okay, so there is a number of use cases, that are demonstrating very impressive results. So the surrogate models do as good a job as the physics model in terms of this very early elimination of design alternatives, but it's computationally very, very attractive. So one example that's related to these use cases, one is about deformation, right? Deformation. This was done the study was done on the mitral walls, that are as complex geometrically as semiconductors. So one study actually showed that if you do this regular simulations, so it could take some 20 CPUs and it takes 3 hours. 3 hours. But then if you pass the simulations through the surrogate model learning, right, say 500, 540, enough amount of iterations of learning, then with just one CPU, and within a fraction of a second, actually, it will give you the results that are as good or close enough. So this is the revolution, actually, that AI is going to bring in semiconductor, be it design, chip design, or manufacturing process design. Okay. You're studying changing the world with chips, and we need to approach it sustainably, right? So I want to go again back to the materials aspects here, sustainable materials. This thrust on getting the materials right. PFAS, some of you might have heard about. PFAS are polluting the environment quite a bit, and they are pervasive actually in semiconductors over time because of their usefulness. But now, the time has come to identify alternatives. So there are, again, simulation modeling technologies that make it possible. Also, calibration, right? So how can you rely on all this? If you were to skip the physical test or physical verification, you have to have a certain trust in this digital board model. So calibration is very important, right? That you can trust that the right properties or optimal properties are actually being used in the simulation. Okay. There is this whole discipline around life cycle assessment, LCA. Okay. So this is an example of not of a chip, but the chips and many other technological components placed in a consumer device, right? And so you have this life cycle approach of what if I change one process by another? What is the impact on carbon, energy consumption, water consumption, or waste, right? And you do this on a product level, but you can do this on an operational level, manufacturing, be it a manufacturing plant or otherwise, right? So this is a facility in operation, again, data centers or manufacturing plants, again. A lot of the sustainability impact actually comes from manufacturing. So there are digital twin technologies that can help here. So this is just one visual of the factory performance, but from a sustainability standpoint. This is again an idea that is currently being explored with the Berk Nanotech Center. Again, what if we make the equipment sustainable, net zero actually, by having a good visibility into its energy consumption or the kind of gas emissions or other waste that goes on there, and doing it at unit level and then cascading it up into a lab level, and what if we make the lab as carbon neutral, for example. So digital twins for sustainability. Okay. Kind of went fast, a lot of examples, but this is So the vision is, this is one vision actually to see the future of the semiconductor, and we could call that as a semiconductor virtual universe, wherein all these digital twins that we talked about sort of come together. They're connected, they're integrated, they come from different sources, but they ultimately serve, they connect the ecosystem, from the chip design all the way to the end customer, everything in between, and serve these very critical use cases around workforce development, infrastructure sustainability, fab-level process research, and new kinds of application that will become possible with next generation and Apple Vision for new kinds of devices. Right? Again, just keep seeing what's happening in the field of digital twins. This is just one source of more examples. You can take a look what the digital twins are. I think the more concrete you see, rather than definitions or textbook-like approach, when you see these examples for across the industries, you'll get a better idea. So I just wanted to leave you with kind of 3 takeaways. If you are already in this class, you're intrigued by semiconductors and you're intrigued possibly by digital twins and the digital technology, what's in the store, right? When you finish your education, advanced education, and want to get into semiconductor industry. So one thing I see is that this become really a multi-scale system world. So it's not a chip standalone, right? And it's not just understanding the physical design or physical process of chips, but it's also understanding in totality the integrated aspect of virtual plus real. So because virtual is like a distinct set of technologies we just saw, the understanding of physics and materials, data science, plus the understanding of what is in the physical design and manufacturing. So the system world is critical, all the way up to the end products. You have to see what I'm designing or building is going to do in the product or system that it is going to be placed in. And by the time, when you join the workforce, industry, academia, or otherwise, there are going to be new roles. I mean, we cannot even anticipate. We're just starting to see, what if, there is a need for digital twin architects, system engineers, but, who are multi-domain, and sustainability. We don't have a solution as of now. We need to figure it out. It's going to be part of your mission also to see what is doing sustainable the first time, not after. After is very difficult. And then ecosystem, we cannot do it alone, right? We have to work in a collaborative mode. Industry is very commercial and innovation, IP concerns are there, but ultimately there is now a lot more openness to work in this kind of ecosystem approach, from industry all the way to standards. Right? So it's a fascinating time for you to be part of semiconductor revolution, and there are, again, I'm coming at it from a software perspective, digital platforms and software, and so we do have a lot of people who are joining fresh, with these type of backgrounds that we just discussed, physics and different types of sciences, data also, and yeah, it's really for you to make your own impact. Actually, it's really beautiful time right now. So with that, I just want to pause here and take any questions.
All right, does anybody have any questions? Okay, go ahead. Apparently the mics in the classroom are working now, so you can just talk.
All right, sounds good. Thank you, Mr. Pandit, for coming today. We really appreciate your discussion. My question, maybe outside of the realm of the semiconductor industry, and just more about general industrial things. So, say that some kind of industrial center has maybe an issue that might be outside of the scope of your factory simulations. Say, for example, some kind of saw has a mechanical issue where it stops running in the middle of the line. And the actual issue was there was a loose screw in gearbox or something. Those very small issues that might not be picked up by the system, by the systems and the software you use, how do you or what's like the plan to maybe bridge that gap? What systems exist to help engineers find these issues? Things like that.
Yeah, there are many tool sets actually that are being made available to people in the shop floor or maintenance, right? So first of all, there is expertise that is irreplaceable. I mean, with expertise, you can detect and diagnose issues. But now we talked about the AR, VR type of technology, right? So we can, so rather than relying on the conventional sources of knowledge or how to diagnose that issue, you have this rich augmentation of work instructions or user manuals, that now thanks to the AI copilot technologies, you can very, very contextually find the right piece of advice or diagnostic information and be able to apply that, right? Now, beyond that, again, depending on some of the example that you mentioned, you could have more advanced technologies that are doing in the metrology or inspection, wherein not just from a exterior standpoint, you can actually scan for the issues, but there are technologies that can actually, for example, even in semiconductors, you may have some internal defects actually in the wafer, right, porosity and others. So those type of issues could also be detected, with newer technologies. If I think about it. Yeah.
Could I maybe ask another question based off that? What about for factory simulations? What about simulating possibly unknown or repeated issues? Say that issue that may have not been come up before, and maybe it's a first time issue on factory floor. How could that be simulated, and how could that be worked?
Yeah, I think you have to reach a certain level of it's a critical mass of digital models. For instance, we in the fab example we talked about the models of the materials, the processes, the various equipment, the flow that actually goes through the layout, the lines. Then you have the infrastructure also that is supporting that. So once you have this critical mass of connected set of models, then it actually lends itself to problem solving, right? So there is a certain core in investment also that needs to happen up to a point wherein it starts to provide you those answers. And prior to that, then you can conduct these stuff, very individual kind of project-specific studies. If you want to just study the material handling system, or if you want to just study one equipment, then those are specifics. But in order to do something at the factory level, optimization level, then you need this type of connectivity of the digital twin models that we just talked about.
Any other questions?
Yes.
So thanks for coming today. My question is, so this software seems very computationally intensive. So is this something? I guess more of a simple question. Is this something that you host on your own, maybe servers or something that the customers can then access, or is it something more that they could run locally?
Yeah, that's a great question. So these are indeed computationally intensive resources. So there are different mechanisms. There's something called HPC, high performance compute, and there are a number of configurable options, wherein you can choose where the resources are and how you deploy them, the workload. So basically, different types of simulation use cases, you can organize and execute them. There is a whole discipline around that for HPC. So that is, and now we have public cloud, with even more scalable compute resources. So it's definitely a focus. And plus, now more and more, the more complex physics comes, it's going to require more resources.
Any other questions? Okay.
I'm wondering how long does it take to make from a digital fab, for example, produce one, how long does it take to make it? What's the process and how long it takes?
Yeah, that's interesting actually. So there is this initial curve, wherein there is a learning, which is not a digital effort, but just to get into that mindset of digital, right? And then there is the data acquisition aspect. So we had to start from the 2D drawings, reverse engineer to 3D, then getting the equipment. Again, you have to work with the equipment vendor for the 3D models. You saw kinematics also there, and so you have to model all this kind of articulation on that. Then there is the establishing the flow, and then the whole kind of enabling the use cases for training purpose, for if you want to do experimentation. So once you do that, then so for back to the Purdue, the Burke example, it took about 3 months actually to build something like that. But then the subsequent demos that you saw there, the gowning and the safety procedure, or making that available in a headset, very incremental.
I think we got time for one, maybe two more. All right, yep, Jared.
So for the learning process for someone new working with the software, what does that look like, and what's the best way do you think that someone should go about learning how to use the software?
First of all, I think you have in the educational environment access to the same commercial enterprise level software that engineers use in their industrial settings to you here, right? So that's the accessibility is there now, and plus due to the platform approach and accessibility on a cloud environment, it makes it very, very accessible. The other thing you need is then data sets. Okay, so you need not a super complex real life example, but something that represents reasonable complexity. It's a problem worth to solve that you cannot solve using your traditional method. So you need to find the data sets, right? And then most of these examples are kind of multidisciplinary. So you might have to think about a small team of people who will bring in that expertise. Somebody who's good at simulation solvers of a certain kind. Different. Maybe somebody is good at mechanical. Someone is good at in plasma. Who knows materials, and then the whole software environment upskill in terms of accessibility, cloud, and all those things. So it's really once you have this data set and teaming, things can go really fast actually.
All right, I think we'll call it there. If you have any more questions, are you able to stay for a couple minutes after?
Yeah, absolutely.
Awesome. All right, so he'll still be here if you have any more questions, but let's give him one more round of applause.
Thank you.
Thank you for coming out.